Okay, so today we're going to talk about the Venturi effect. So what is the Venturi effect? It's the effect that we've already started talking about, but whenever you have a pipe diameter decrease, or in other words, the area for a fluid to travel through is decreasing. The continuity equation tells us that the fluid velocity is going to increase. Now, as we already said, fluid velocity doesn't increase for no reason. It has to be some force to increase that velocity to provide some acceleration. So that force has to come from somewhere, and in this case, it's going to come from pressure. So the Venturi effect is really just a decrease in pressure and an increase in velocity. But this has many effects that we see in industry and affects and is exploited in several ways that we're gonna to look at. So as we can see in this animation, we have high pressure, low velocity fluid pushes the flow ahead of it, increasing the velocity. Okay. So the energy, the pressure energy is being converted into velocity through the smaller section of pipe. And then, of course, that velocity then increases or slows down and imparts that energy back into pressure upstream. So what's the applications of this? Well, for one, we can use it to and it's used in a carburetor to put fuel into an airstream. This process is called atomizing. Basically, what it does is, as the air comes through, there's a decrease in area, okay, and then that decreases the pressure, and because of the increase in velocity. So that decreases the pressure, and in effect, it will pull fluid from another part of the carburetor through a jet and into the airstream. The jet, the fuel that gets put into the airstream is very, very fine particles, and it's in that effect is called atomizing. You can do air to air. You can do, so in other words, or I say air to air, it could be gas to gas. So there can be a gas pulling another gas in. You can have a fluid pulling another fluid in. In this case, you have a liquid pulling another liquid in. In this case, you have a gas pulling a liquid into the gas and atomizing it. So you can mix different materials together by using this effect. Okay, here's another example of atomizing. You're taking high or compressed air, and you're pulling a fluid. In this case, it could be paint, and it's a very common application would be paint. The paint is pulled into the airstream. Okay, again, another effect of the Venturi. Another application of the Venturi effect. Another one you'll see is a vacuum generator. So basically, what you have is an airstream that's moving and actually pulls a vacuum. So the application of this is if you, for example, want to create a vacuum to pick something up with a end effector on, let's say, a robot. It wouldn't be a very practical application to create a vacuum with some compressor when you have compressed air available. So what we use is a vacuum generator, and it uses the Venturi effect. Basically, there's check valves, and as the airstream moves through, it creates a vacuum, and will create a pressure or a vacuum. On like a suction cup or something of that nature. Now it's pretty expensive in terms of airflow in order to create a vacuum that's continuously pulling vacuum. So in other words, if your suction cup it needs to be able to suction to whatever it's trying to suction to, and then of course it will stay there with the check valve, keeping that vacuum. But the without if you for small applications where you're not having to pull high volume of air under high vacuum, a Venturi vacuum generator is a very easy way to get vacuum. Of course, we've already talked about this a little bit, but a flow meter can use a Venturi tube, and so as flow moves through a smaller section of pipe, you have a pressure drop, and then of course we read the difference of pressures and we can calculate what the flow rate is. So we've already done this through application of Bernoulli's equation and continuity equation, but what I've done is I've derived two equations that will be useful. One calculating flow rate based on area, pressure difference, and of course the density of the fluid. And then the next one is a difference of pressure differential, based on flow rate, area differential, or different areas, and then of course the density of the fluid. I could derive these for you if you would like at some point. If you have questions about how to do this, I would encourage you to derive them yourself, just to get a little bit of algebra practice and understand where exactly it come from. But I won't be doing that now. But aside from the fact it'll take quite a bit of room to do that. But the two equations that you're deriving it from is just, of course, your H1 plus P1 divided by the specific weight of the fluid plus velocity 1 squared divided by 2g equals H2 plus P2 divided by specific weight plus V2 squared divided by 2g. And of course these are 0. And then from there's another equation you'll also need, which is the continuity equation. A1 times V1 equals A2 times V2 equals flow rate. So those are the two equations that you're going to need. And if you so inclined, I would suggest that you derive that for yourself, just so you can see how it's done. All right, so a couple of examples here. So what's the theoretical flow rate of a Venturi tube or flow through a Venturi tube with an upstream diameter of 1 foot and a downstream diameter of 0.75 feet? If the upstream diameter is 60 psi and the downstream diameter pressure is 58 psi, and the specific gravity of fluid is 1.2. So first thing is, what's our area? Area for 1 is going to be 0.78 foot squared. Area 2 is going to be 0.44 feet squared. We've done area for a while now. Hopefully you don't need help with that. Pressure 1 is going to be 8,640 psf, or pounds per square foot. And pressure 2 is 8,352 pounds per square foot. So remember, when you're in PSI, pounds per square inch, whenever you're using this equation, everything needs to be in pounds per square foot, slugs, feet, seconds. So that need to be your pounds, need to be your base units in order for this to work. If you are in other units like PSI, you may have issues. So, and then the last thing is the density, which again needs to be in slugs per foot cubed, and in this case it's going to be equal to 2.328 slug per foot cubed. Okay, so the equation is pretty straightforward. It's just Q equals area 2 square root of 2 times P1 minus P2 divided by the density 1 times 1 minus, that'll be area 2 divided by area 1 squared, and that's it. So, sorry about that. I'm trying to recall the equation. All right, so all we have to do is fill in the blank in and then answer and solve the equation. So it's actually pretty straightforward. It's not too hard. So Q equals 0.44, which is area 2, times the square root of 2 times P1 minus P2, which is 8,640 minus 8,352 divided by 2.528 times 1 minus 0.44 feet squared divided by 0.78 feet squared, and all that squared. So Q will be equal to 0.44 times the square root of 576. This is PSF, so pounds per foot squared. I'm going to go ahead and just write out that this, because it's going to be helpful for us in a second, that is actually going to be equal to a slug foot per second squared. So pounds per square foot is just a slug foot per second squared. And then is going to be equal to 1.58 slug per foot cubed. So if we look at what our final units are going to be inside of here, right there, it's actually just going to be equal to a foot squared per second squared, which makes sense because this right here is feet squared. So when we square root it, we're going to get foot per second. So we're going to get a velocity times an area, so we should get a flow rate. So Q equals 0.44 feet squared times the square root of 364.5, which is equal to 19.09 feet per second. So Q equals 8.4 cubic foot per second, which is going to equate to about 3,769 BPM. It's quite high. What you're going to find with this problem and some of the other examples that or questions that I've given you in your homework is that some of these numbers are quite large. The areas I've given you is quite large to try to compensate for that a little bit. And the reason why is because typically your pressure difference is going to be quite low. There's going to be a very small pressure differential. And so if I start giving you, really small pressures like, 0.1 psi or something of that nature, that's going to be, make the equations a little different and maybe make it a little harder. So all I've done is just try to use even numbers, and so some of your numbers might get quite large. Okay, so this time it's asking for a pressure differential, and it's going to be the pressure difference in a Venturi tube that's passing 1,000 gallons per minute and has an upstream diameter of 1.5 feet and a downstream diameter of 0.5 feet. And the specific gravity of the fluid is 1, so it's water or something like water. So first thing we're going to do is get our areas. A1 equals 1.76 feet squared. A2 equals 0.196 feet squared. And our flow rate is going to be equal to 2.22 feet cubed per second. And our density is, of course, just 1.94 slug per foot cubed. This time, pressure differential is equal to, go our density, divided by 2, times 1 minus A2 over A1 squared. And then we've got Q divided by A2. So again, you're going to look at a very similar equation. All we got to do is fill in the blanks. So our density is 1.94 slug per foot cubed divided by 2. 1 minus area 2, which is 0.196 feet squared, divided by 1.76 feet squared, times 2.22 feet cubed per second, divided by our area 2, which is 0.196 feet squared. And if we do the math on that, we're going to find out that we've got 121.6 slug per feet cubed times 0.9875 times 11.32 squared, and that's just going to be equal to 121 PSF, which is a 0.84 PSI. So as you can tell, even with a very high flow rate of 1,000 GPM going through a fairly small pipe, foot and a half and half a foot, our pressure difference is still quite low. So, and that's typical. So a lot of times these flow meters actually have a they actually do the calculation for you. They're just going to give you a flow rate and it could be current, so 420 milliamps or 0 to 10 volts or something of that nature. Could be digital. But it's good to know the reason why we talk about this is so we know the theory about how it works. There are things that we need to keep in mind. For example, if you have large pipes, you could have a flow pattern, and we haven't really talked about flow patterns a lot, but flow pattern where if you've got high velocity fluid moving over your pressure sensors, but low velocity fluid elsewhere. So in other words, you have a flow path that's non-typical, and that could be because you've got your flow meter right at a bend or something. Then you can get different pressures that give you flow rates that are not what you expect. So the moral of that story is don't put your flow meter right next to a bend. But there are other things, so that's the reason why we need to know the theory behind it. If you have any questions, let me know.